Hey guys, thanks for tuning in to another Q&A video on ForgottenWeapons.com. I'm Ian McCollum, and today we are going to be talking about firearms manufacturing. Having just recently gotten back from SHOT Show, I thought that would be an interesting topic for today's Q&A. So I have 4 pages of questions from the fantastic folks over at the Forgotten Weapons Patreon. Ooh. And as usual, our Q&A video today is brought to you by Kiro. Today's Kiro whiskey is in fact Kiro gin, which actually has an interesting tie-in to manufacturing techniques all by itself. So when you start up a whiskey distillery, like Kiro up in Isokiro, Finland, you produce batches of whiskey, but before your raw spirits can be actually called and sold as whiskey, they have to age for several years. In the case of whiskey, 3 to 4 years. So what do you do in the meantime? You need something to generate income for the distillery. What you typically do is produce something like gin or vodka that does not have any aging requirement. Now, Kiro actually makes an aged gin, which is fantastic. That's their dark gin. But today we're taking a look, well, I'm taking a sip of their standard Kiro gin. This is the very first product that they manufactured. This is what got them, in fact, got them noticed as a distillery first, because back in 2015, the International Wine and Spirits Competition gave them a Best in the World Gin and Tonic Gin for this gin, and then gave it to them again just last year in 2025. So that's what I'm trying here. They recommended it with cranberries and rosemary. However, cranberries, as far as I can tell, do not exist in North America outside of approximately October to December. So I don't have cranberries, but I do have rosemary. It actually grows in my yard here in Arizona. And this is fantastic. This is a nice juniper and earthy flavors forward gin. Mixes really well. It is in fact really good in a gin and tonic as well. Affordable. And right now, if you're interested in it, you can pick it up for 10% off. Actually, you can get any of their spirits 10% off if you use the code ForgottenGin10 in their checkout on their US, German, or Finnish web stores. I'll have a link down in the description text. All right, so let's transition from gin to gun. And our first question here is actually sort of a question that I got from multiple people, in particular George and Keith both. Keith asked, in your opinion, could the United States recenter its industrial manufacturing base like it did in World War II, or is that not a possibility with modern military equipment? George asked something very similar. If we got into a shooting war and the Army needed like 2 million M17 pistols and 5 million M7 rifles, etc., would the Army have the ability to farm out manufacturing to manufacturers other than SIG? Not just the legality, but does the US firearms industry have the ability to produce the numbers that we would need? What about optics? Would M7s be going out the door with irons only? I am not an expert in industrial policy. I don't have really an expert's knowledge of the current US industrial base. But what I do know is manufacturing, it is simpler today to transition from manufacturing one thing to manufacturing another than it was in World War II, because basically all manufacturing today uses CNC machines, which are readily reprogrammed for any number of, basically anything that you can fit into the machine physically, you can make in the machine. There are going to be, obviously you'll have to do programming, there will be tooling and fixtures required to hold your parts while they're being machined, and there will of course be different cutting tools required for different particular operations and cuts and procedures and such. But the way manufacturing worked back in World War II, a single CNC machine's job would have been done by a whole bank of individual milling machines, each with one very specialized cutting tool that would make one cut on a part. So you would put, let's say you had a receiver for a gun, you would put the square block of metal in the first machine, run it through that machine, it would make one cut, one very specific profile. You would then take that and put it into the next machine, which would make the next cut. Today's CNC machines, you put the block in once, and the tool comes in and makes one cut, and then another, and then another, and then another, all without having the part having to be handled by an operator. So reconfiguring a CNC machine to go from making some part of a car or anything really to making some part of a gun is not that difficult of a process. Now, we don't really have huge firearms industrial companies in the US today, the way a lot of them existed during World War I and World War II. But, and so actually I should say, like, during World War II, the US gun companies that existed were very quickly completely filled with manufacturing orders to the maximum limit of their production capacity. And the US government and military turned to the non-firearm industry to take up the other manufacturing that was necessary. And that's why you get things like the Rockola jukebox company making M1 carbines, and GM, various divisions of General Motors making all sorts of different guns. Like the guide lamp division, the headlight division of General Motors made M3 grease guns. Frigidaire, the refrigerator company, made M2 heavy machine guns, that sort of thing. That could absolutely happen again today. And what we might lack in really huge, like massive industrial complexes, I think we make up for in a lot of small scale, much smaller shops doing batch work, especially for things like the aerospace industry. These are shops that have maybe not 100 CNC machines like a huge firearms factory or a huge automotive factory would have, but they have a couple of CNC machines. And products for today's parts interchangeable guns can be very easily farmed out. In fact, the way a lot of manufacturers today do this work is they subcontract all the different parts to a network of different small-scale suppliers who will do a gun part today and a car part next week and an aeronautics part the week after that. The World War II comparison here would be the way the British did Sten gun manufacture. They called it, I believe, the pedal scheme, where they subcontracted the different parts out to a lot of very small little shops. Well, it'd be very easy to do the same thing today, and it would be more effective than it was for Britain in World War II. So yes, I think we could very much scale up our manufacturing of firearms if such a thing were necessary. Making gun parts is not fundamentally any different than making other industrial parts. There isn't any real special sauce to firearms parts. You will often see gun parts manufactured by aerospace companies, or rather aerospace and gun parts often mingled in the same facility, done by the same shop, because they tend to have relatively similar requirements for tolerances and quality control. And yeah, that would actually work pretty well. As for optics, I don't really know. If we needed 5 million M7 rifles, I can guarantee they would not be going out with, was it M157, like super complex computerized scopes. Those are not going to scale up and manufacture real quickly, but the manufacture of basic magnified or unmagnified optics probably could be. That I'm not entirely clear about exactly which components need to come in from overseas. And then you have the question of, well, okay, who are we going to war with? Countries do not do wartime mass manufacturing necessarily all by themselves. There's a reason that the United States got the nickname of the Arsenal of Democracy. It's because in World War I and World War II, we didn't just make guns for us, we made guns for everybody who was on our side. And the idea of international munitions trade supporting the requirements for a country that goes to war and needs a huge quantity of munitions materials is very much alive and well today. Frankly, we see it in Ukraine at this very moment, kind of talking about exactly what this question is. So if the US needs to massively scale up production for ourselves, chances are we will have hopefully we will still have international partners willing to help supply the components that we can't necessarily scale up manufacture here in the United States of. Let's see, our next question comes from Buntline, who said, over the years, you've covered metalworking techniques for firearms manufacture quite extensively and polymer molding to some extent as well. But until the latter part of the 20th century, there was also a lot of woodworking involved, which has never really been mentioned. He's got a point there. How did they turn out millions of identical Garand or SMLE stocks? What sort of machine was used to do that? And how were complex curved shapes programmed for repeatable production? And did they need to do anything special to secure a supply chain of suitable timber during high-rate wartime production? Let's start with the timber. Yeah, they absolutely did. Timber has to be dried before it can be used for wood stocks. If you make stocks out of wood that is still too moist, too fresh from being cut, it will swell and shrink and do weird stuff shape-wise and cause problems. You do have to have it suitably dried. So naturally dried wood is best, and during wartime, typically the first thing that companies would do, or arsenals would do, is use up stocks that they had already laid aside of properly dried wood. They would also then start working with kiln drying to accelerate that drying process. And then the next step is using less desirable species of wood. You know, you'd like to use good, super high quality, dense walnut, but when you run out of dried walnut, well, maybe you can get some of these other types of wood that will work. They're not as good, but better to have a substandard, you know, a lower grade of dried wood than wet walnut that isn't going to be acceptable at all. So yes, that sort of thing was an issue, and that's why you see a lot of substitution in woods across long-term production schedules during wartime. As for the machine to make them, that is a super cool question, and it's frankly something that I should have done a video about before. The tool in question is called a Blanchard lathe, which isn't technically a lathe. It was invented by a guy named Blanchard in 1818, or at least in 1818, the Springfield Armory put it into production. Blanchard developed it working for a shop in Springfield that was making stocks for the US government at the time, and then Springfield adopted his technology, and it became essentially a machine copied and used by everybody globally for firearms production. And what it did, the way you programmed it for a stock profile was you made one stock by hand and you clamped it in one side of the machine, and then it would rotate the sample stock. Well, you clamp in the finished handmade stock, you clamp in a block of wood that's the rough overall shape of the stock, and then this machine has on the blank has a spinning cutting wheel, and on the handmade stock it has essentially a tracking pointer, a finger that sits on the stock, and as you rotate both the stock and the blank, the finger traces the outline of the model, the base design, and then this rotary cutter follows that profile, and you essentially just run the cutter up and down the stock, and you rotate them both, and it duplicates the model that you have clamped into the other side. So I say it's not a lathe because you don't have, a lathe has a fixed cutting bit, and then you rotate a part and you just like push the part into the bit or the bit into the part. This actually has a rotating cutter that moves around the component while the component is locked into a single axis and rotates so that the cutter can access 360 degrees, the whole profile of the stock blank. Blanchard lathe was a fantastic machine. Blanchard was a perennial inventor. Like, he started off his career at the age of 18. He and his brother invented a machine that made tacks that became quite successful and made him some money. He would go on to have a whole bunch of different patents. Like early industrial age inventor coming up with cool machines to do specific tasks. And the Blanchard lathe was the one that ended up best remembered with his name on it. If you would like to see one, I believe there is only one original Blanchard lathe surviving, and it is at the Springfield Armory National Historic Site Museum. It occupies a place of honor right smack in the middle of the public side of the museum. It's a big old machine, and if you're interested in early industrial age mechanics, it is a super cool thing to take a look at. So I have a picture of it, but I didn't have time when I was there at Springfield to do a whole rundown video on how the thing worked, but I should. All right, next up, Dalbunoski says, are barrels always screwed into the receiver/locking piece, or is there another way barrels are installed into a gun? Threaded in is one of the most common ways. However, it is also not uncommon for a barrel to be pressed into place. Usually what you'll do is have a very tight press fit that you press it in while measuring headspace. Once you've got the headspace correct, you then drill a cross hole, put in a pin, and that locks the barrel in place. AKs, classically, are done this way. The AKM has a pressed and pinned barrel. So you'll find some other methods. Like, it's not that uncommon to use a heating and cooling element if you're going to press a barrel into place, especially if you want to try and do it without having the barrel pinned as well. So if you heat the receiver, it'll expand, not a lot, it expands a little bit. And if you super cool the barrel, it will contract. You can do that and then get a tight press fit. And when the two components come back to a temperature equilibrium, they might as well be permanently fused together. They're not, but they are very, very tight and very resistant to the barrel slipping out. There are some other methods, like there's clamping sometimes. When you have quick change barrels, you will have locking lugs, like rotate the barrel part way, or locking ledges, clamps that hold it in. There are a bunch of ways. Threading's the most common because it's a pretty simple process that's pretty well understood, and Especially when you have guns where there isn't a gas port, threading is a nice easy way to set headspace as you turn the barrel in without, you set the barrel in place, set the headspace, and then you put on the sights. So you don't have to worry about the barrel always having to be indexed to the exact same spot as you're setting headspace. If you've got something with a gas port, you have to have the gas port in a specific indexed position, typically like the very top or the very bottom of the barrel. And so pressing makes sense here because you index the gas port where you need it, and then you press the barrel into the right position and then pin it in place. Next up, Robert says, there seems to be a decline in experienced gunsmiths. They've been an important part of the firearms industry by providing repair, modifications, maintenance, service to gun owners. Are firearms manufacturers prepared to provide more after-sales service in the future? I know from personal experience that Ruger has a dedicated service department that has an excellent repair policy for most of their legacy firearms. I think to some extent, experienced gunsmiths have been a rare breed for a very long time because there are kind of two different categories of gunsmith, maybe three. Like you've got at the far end of the spectrum, you've got the classical like German, Austrian, maybe Czech gunsmith, where they make guns from nothing. Like that's their job, is they make a totally custom boutique firearm from total scratch. And that's the educational process. At the other end of the spectrum, you have sort of your base level of, I run a small gun shop and we have a gunsmith on staff, but the work that he's called on to perform is cleaning a gun for a customer who just doesn't want to bother and wants to pay someone else to clean the rifle, or installing a scope and getting it zeroed before hunting season, or reassembling a gun that a customer took apart foolishly and can't figure out how to get back together. So those things are much more along the lines of, like, if we consider this in automotive context, that's like Jiffy Lube. That's I'm going to take my car to a drive-through sort of place to get a very basic level of service that 50 years ago is probably the thing that you would have done yourself most of the time. The classically trained European true gunsmiths are like the guys designing F1 race cars, and then in the middle you've got the guys who are capable of, or who do, firearms modifications, custom work. I'm very lucky to have a couple of guys like that relatively local to me, down in Tucson at Diamondback. And they can do some really cool stuff. They make custom parts, they can modify things. But there's really not a lot of call for that work in the large-scale firearms industry, I don't think, because what started off, like the reason that you would need a firearm repaired classically is because, well, something broke, and so you need to have a new part made or have the existing part repaired. Today's economy is much more based on the parts are individually inexpensive to manufacture. They're all perfectly interchangeable. There's no hand fitting required. And so the repair process isn't so much any handwork to take the old broken part and fix it. It's usually just, oh, the part broke, we're going to put in a replacement part. Like the same thing, we're just putting in a new one. The trigger linkage broke. Well, weird. Must have been a manufacturing flaw in it. Replace the trigger linkage. Not go in there and weld the thing back together and then polish it smooth and refinish it. That's 100-year ago gunsmithing, perhaps. Today, like, firearm repair isn't, correct me if I'm wrong, gunsmiths, but it isn't really that much of a thing. It's put in a replacement part for the part that broke. And I think a lot of firearms manufacturers, while they may have to have a repair department to do a little bit of that work, most of the time what they want to do is get the gun back in on an RMA, replace the broken part, and send it back out. And the less hands-on time they have to spend on that firearm to get a fully functional, proper, new equivalent back to their customer, the better. Hands-on time costs a lot of money. And whether the company is paying for that or the customer is paying for that, nobody really wants to be the person paying for it. They would rather have the less expensive solution, and that's just put in a new part. So yes, to sort of circle back to the question, I suppose, gunsmiths are in relatively short supply. Finding a good gunsmith, if you want to do custom gun work, finding a good gunsmith to do it can be a trick. There aren't going to be a lot of them. Expect them to have relatively high prices and long wait times because they are highly in demand, because it's also a skill that takes a long time to really develop. You'll find a lot of these guys are crusty old dudes who've been doing it for 50, 60 years, and they're really good, but it's going to take them a while to get to your project, and they're going to charge you more than you would like because there's not as much call for people to get into this business. Now I'm kind of rambling, and so we'll move on to the next question. All right, Lazar says, if a country today were in a similar position to the UK in 1940, i.e. needing to domestically produce inexpensive but effective small arms from scratch as quickly as feasible, would the result look a lot like a Sten gun, a modern service rifle, or something completely different? Well, I think it depends on exactly what the details of the situation are. I actually have a video that I did a while back on the idea of what would a last-ditch M16 look like? If the M16 is in mass production and we're 5 years into a war and the country's been overrun and it's like crank them out as fast as possible, what changes get made to the M16? So I will link to that video down in the description text. You can check that one out for that aspect of it. If this is a much smaller scale thing, you could think of perhaps the breakup of Yugoslavia, the wars between the Serbs and the Bosnians and the Croatians. The Croatians in particular didn't have a lot of guns, and they had to do small scale, very rapid, anything is better than nothing sort of manufacture, and you in fact got a lot of things that kind of looked like a Sten gun. I have videos on a bunch of those Croatian designs, submachine gun designs from the 1990-1991 period. 9mm submachine guns will always be a common element in a situation like this because they are simple to manufacture. They use ammunition that is readily available. There's a lot of sort of this stuff out there to be copied, and it's a militarily viable thing. 22 rimfires, a little too weak to be militarily viable. Once you get into rifle calibers, you need locking systems. 9mm sits in this position where it's ubiquitous. It's powerful enough to be useful from a military perspective, but low power enough to be usable in simple blowback firearms that are easy to manufacture. They don't require that much in the way of high strength specialty materials. So I can certainly see 9mm submachine guns kind of Sten-like, whether they look like Stens or they look like HK-UMPs or something else entirely, really just depends on what manufacturing processes are available to whoever it is who's trying to actually build these things. So, like, for example, one or two of the Croatian guns used molded polymer bodies because the companies making them had polymer molding tools, and so that was something readily accessible to them. Others used stamped sheet metal because they had presses available to them. And it's conceivable that if you ran into a company that didn't have molding tools and didn't have polymer processing tools, but they had a big old bank of CNC mills, well, the most effective thing for them might be to make CNC milled receiver 9mm submachine guns. Not because it's the theoretical best, but because in their specific limited set of circumstances, that's the path of least resistance to the gun. Next up, we have ACC, who says, what quote-unquote lost manufacturing technique, something that few manufacturers do anymore and don't have the money to tool up for, most negatively impacts the ability to innovate and experiment with new ideas? I don't think there is one. I don't think there really is any such thing as a lost manufacturing technique for any reason other than being effectively fully replaced by some other manufacturing technique. So, for example, there are very few shops out there, I think, that still have large banks of manual shapers that each have one specialized cutting tool to make a single part in large volume, because CNC machines have completely replaced that and are essentially better in every way and offer a lot more expanded capabilities. Now, does the lack of, call it 1920s era milling machines hinder our ability to experiment and innovate on firearms design? Nope, not at all. CNC is, again, far better for that in every way. So I don't think there's really, the things that are best, the two biggest tools, I think, for innovation and experimentation First off, one is going to be computer numerical design, being able to model things and test them just in a data form on a computer. That's massive. When it comes to the physical manufacturing, the two best tools are 3D printing and CNC machines, because both of them allow you to iterate far more rapidly than a factory 50 or 100 years ago could have done. All right, next up we have Benjamin, who says, how much does metallurgy play into design? Is it a case of there's 6 different types of steels within one gun, or is it decide on 1 to 2 and stick with them through the whole thing? Well, like many questions in this Q&A, the answer is going to be kind of depends. You want to have as few as possible, just because the fewer different materials that you have to source as a manufacturer, the easier everything is going to be. However, every part obviously has to be made of a material that's suitable and functional for its purpose. So if we take an AR as an example here, we've got actually a fair number of different materials in here, and none of them can really be substituted, and you wouldn't really save anything by trying to simplify and reduce the count. So first off, we of course have a high quality, high strength steel for the barrel. Has to resist chamber pressure and such. For the receivers, the receivers in the AR do not bear pressure directly, so they don't have to be a really high strength material. We can make them out of aluminum. That will reduce the weight of the final product. Aluminum is also really nice and easy to manufacture, to machine. So we're going to get better life out of our cutters. We can manufacture the parts faster if they're made out of aluminum than if they're made out of steel. So aluminum is a really good choice for that. In fact, that's what the gun was really designed around. We're then going to have a couple of other steels. So for example, the gas tube has a very specific role. Like that thing has to be a thin hollow tube that is filled with very hot gas. The pressure is high as well, but it's not, it's a different, subtly different set of requirements from the barrel, which is also a tube full of high pressure gas. But they work differently. You're not going to want to use the same materials in the two of them, largely because of the way that the two parts are manufactured. You're going to be turning, like hammer forging a barrel, turning it on a lathe. Gas tubes are made very differently. So 2 different steels there. You're then going to have, for example, your front sight block. This isn't pressure bearing. It doesn't have any particular temperature requirements, but it's a fairly complex shape. And so we're going to want to cast this part. So we're going to want to use a steel that is suitable for casting. As opposed to, let's see, what's a good example here? The dust cover. This is a part that we're going to manufacture by stamping because it's a thin piece of sheet metal. And so a material that is malleable and good for stamping is probably not going to be the exact same grade of steel that is good for casting in the front sight block. So there's another different steel for us. We're going to have some things like roll pins, parts like the fire control parts, the hammer, the trigger, parts in there that are either going to be stamped or milled, possibly forged in a few cases, probably not in this case for sure, but those generally, you know, if it's a small milled part, your requirements for it are pretty minimal. You might use the same steel that you use for casting. You're not going to use the same as used for stamping, because stamping is a kind of specialized thing, but you're probably going to have, so that's, what are we at? 1, 2, 3, 4. I bet there's 5 different steels in this, plus an aluminum. There might be 2 different aluminums. Most ARs are made out of 70-75 aluminum, which is an alloy that's a little bit stronger than 60-65 or 60-61 aluminum. The charging handle, I didn't look this up beforehand, but I bet there are a lot of charging handles out there made out of 60-61 because it's a little less expensive. Then we're going to have some polymers, almost certainly the same polymer for the handguards, the pistol grip, and the buttstock. Aluminum for the buffer tube is probably, it's going to be one of these two. 60-61 and 70-75 are really the 2 most common aluminum alloys used. So yeah, there's like 6, 7, maybe 8 different materials that go into this. And a lot of guns are going to be like that. Paul says, I would be interested to know more about manufacturing tolerances. How are they determined? That is an entire field of engineering specialty. How difficult is it to maintain consistent tolerance? How much does it differ by grade or price of a product? It does, definitely. So how do you determine it? Typically, that's basically you conduct an engineering study. You will take your initial drawings of what all the parts are in this theoretical perfect sense. You know, our part is going to be exactly 0.0064 inches, millimeters, meters, whatever, in this dimension, and it's going to interact with these other parts in this way. And you will then actually slowly start to study, okay, if we make part A a little bit smaller in this dimension and part B a little bit smaller in that dimension, do they still interact correctly? At what point do they stop interacting correctly? Okay, now what if we make part A too big and part B too big? Again, at what point do they stop interacting correctly? The goal being to come up with tolerances, a range of measurements for every dimension on every part within which all of the parts are interchangeable. You can take any random piece within that range of dimensions, and it'll work when assembled with every other component of a firearm. And maybe you don't need 100%, maybe you're going to go with, we want 99% compatibility within parts just to save ourselves a little bit of work on this, but it's, for today's manufacturing, it needs to be pretty high. And this is part of why scaling up a gun from initial, like individual handmade prototypes into a production line is a complicated, difficult, and long process. And when we look at it historically, the idea that it would take a year to do drawings on a gun, that's why. It's because there are thousands of dimensions in a single design for a complicated mechanical thing like an AR, and every one of those dimensions has to be toleranced, or else you end up with a lot of parts that don't work together, and you don't generally find out until the guns get out into the field, and then it's like, oh, then you have a massive recall. So don't, like, it's important also to realize that dimension means a lot of different things. It's not just, okay, this is a, you know, the barrel is 16 inches long and it's 0.5 inches in diameter. Every single time there's a feature on that part, it's going to have dimensions associated with it. If you have a radius that's being cut, what is that radius? How much flatter or sharper can that radius be and still work? Distances between datums. So when we have the holes for our fire control pieces in an AR, where are they located? How close are they to each other? How far away are they from each other? It's not just a matter of this pinhole has to be, you know, this far up from the bottom of the receiver. It also has to be a specific distance from this pinhole in both X and Y dimensions. It has to be a certain diameter. You know, the hole, if it's too big, the pin rattles around inside it. If the hole's too small, the pin doesn't fit inside it. Like, there's a lot of data points that go into a dimension. So that can be very complicated. Once you've got all those numbers in hand, then it's a matter of essentially the faster you want to, there's a linear trade-off between how fast can you manufacture parts and how tight can you maintain their tolerances. So there are some dimensions where the tolerance kind of doesn't really matter. Like, you can have a very wide open tolerance. An example here would be what's the angle on the front sight protector wings on this AR? You know, they bend out a little bit, but this versus that, you know, how strict do we need to be with that? With these parts coming out of the cast? Doesn't really matter. And so we're not going to spend a lot of time. We're going to, you know, we don't need to be super precise on that. And maybe to the point that we don't even bother measuring it to check. On the other hand, the dimensions on our bolt lugs relative to the barrel extension, those have to be really good. Like the headspace dimensions, the dimensions that produce the headspace, those have to be really good and really tight. And so you're going to have a machine that makes parts. No machine makes perfect parts. They're all going to have a range of dimensions that come out of the machine. And the trade-off here is when you need to maintain a very tight tolerance, you will either have to reject a lot of parts. You could take a machine that's barely capable of, you know, let's say your tolerance is 3 and your machine will put out a range of 10. You need 4, 5, or 6, and the machine kind of randomly spits out anything between 1 and 10. Well, okay, you're going to be discarding 7 of the parts that come out of that machine, but every 4, 5, and 6 that comes out, you check that thing on a gauge. 5, good. 4, good. 3, scrap. So we're essentially taking 70% of our production time and just throwing it away. But maybe that's a very cheap machine that we already had on hand and it's not usable for anything else. And so it actually makes sense, even though we're only getting 30% efficiency out of it, to just use it for this part. Or you can get a much more expensive, high quality machine that only spits out 4s, 5s, and 6s. And okay, well, that's cool. That's really well matched. I need 4, 5, or 6. Great. Then, you know, maybe you get the next part in that you have to make and it can only be a 5. Has to be right in at 5. At which point it's really, you're talking like, it needs to be between 4.7 and 5.3. Well, now if your machine spits out 4 to 6, you're once again in a position where your machine is a lot less precise than the part that you need to get out of it, and so you're going to be scrapping a lot of the material. Or the other mismatch can also happen. You have a machine that'll spit out 4s, 5s, and 6s, and you need anything between 1 and 10. Well, if that's the only machine you have, great. 100% of its output's going to be good to go, but you're going to be wasting the potential when you could have that part running on a weaker, older, not weaker, but an older, less precise machine, because it fits the range that you need on that part. If there's one fundamental thing here that I think maybe people don't recognize or don't think about, it is that the idea of quality is really kind of variable. Everything does not have to be higher quality. It has to be acceptable, correct quality. Again, how precise do I have to make the front sight wings on an AR gas block? Doesn't really matter. Like, you know, if I want to go make a boutique $20,000 AR and I'll have 0.01 inch tolerances on the front sight protector wing geometry, that's my prerogative, but nobody's going to buy that thing. So the idea of efficient manufacturing is to make the part exactly as good as it needs to be to function correctly. The next question, I suppose, would be, how do you determine this? Are you literally measuring every dimension of every part that comes off of every machine? And the answer is almost certainly not, because that would be impractical. It would take so much time to do the measuring that, like, we wouldn't get any actual work done. So what typically happens is the use of statistics. You will measure a specific subset of the parts that come off the machine. Typically, you're going to be looking at a machine that will, let's say, spit out 4s, 5s, and 6s. And every day you measure 10 parts at random that come off of it, and you record them in a chart. And, you know, over the course of a month, you'll see your part numbers, you know, the dimensions fluctuate. And then let's say you just stop replacing the cutting bit. Eventually that cutting bit gets dull. It starts chattering. Your precision drops. You know, all of a sudden you've got more chaos in that machine. And now you're going to start seeing it throw out a 3 here and an 8 there. And if you're plotting your 10 random parts per day, you will start seeing these outliers that are outside not necessarily outside the bounds of what's acceptable for the part, but outside what you expect that machine to be outputting. And that's your clue that, aha, I need to, like, something's wrong with that machine, I need to check on it, which usually is going to mean something like we need to replace the cutting tool. So that's, like, statistical analysis is a very, very math-heavy, very essential part of actual industrial production. Is there a third part to this question? How does it differ by grade or price of the product? There's also a level here of just practical acceptability. I talked about this with Mike Branson a couple years ago at SHOT Show with optics, for example, although it applies to anything. You can also, as a manufacturer, accept that of every 100 parts, of every 100 complete products that I ship out to customers, some number of them aren't going to work. And if it's a very cheap product and I don't expect people to put much use into it, and maybe it's worth my while to accept that 5% of what I ship out is going to be broken, or will have some defect that will cause it to break very quickly. And if it makes economic sense for me to just replace those, wait for people to discover that they're broken, and then send them back to me, and then I just ship them a new one, which there's still a 5% chance that the replacement will be broken. But that can be a cost-effective program. And if it's, you know, a relatively low priority thing, you know, where people aren't depending on this for their lives, fine, okay. And what that allows you to do is make the whole product cheaper because you are throwing away less of your production time. So again, let's go back to that machine. I need 4s, 5s, and 6s. Well, let's say I just accept that I'll take a 3 or a 7 as well. And I recognize that if a 7 from that machine gets paired up with a 3 from some other machine, the combination isn't going to work reliably. But how often is that random combination going to happen? Not very often. I'll accept that. I'll open up my tolerances a little bit because it means I can make the parts faster, or I can scrap fewer of them in the process, and I can ship more product in the same amount of time and make more money. And if the more money that I make by doing that is offset by the number of broken parts that I have to replace later, then that can be a positive economic decision to make. On the other hand, if you want to be a company with a reputation for like nothing ever, like everything is great out of the factory, you don't have to worry about it, you can depend on this, life or death, Aimpoint actually kind of comes to mind here, then what you do is like you do a lot of checking, you throw out a lot of scrap, or you invest in machines that are more expensive but produce almost entirely parts that are within your tolerance, your required tolerance range, and you ensure, like, you check every piece that comes off the line. Every item gets test fired or test turned on or zeroed or whatever it is for that product. That's going to make the product more expensive because people have to do the work to do that inspection. It means you're much more likely to be throwing out some scrap parts when they don't work, where a lower end company would just ship the one that might not work anyway and assume that maybe someone won't use it, or maybe it'll work well enough for them, or maybe they'll just accept that they're going to replace it when it gets returned to them. So hopefully that answered that question. James says, in some of your videos, you compare early and late production versions of the same guns that function identically but differ in how they're machined to save time and cost. From an engineering perspective, are there general manufacturability principles that guide these changes, or is machining optimization mostly about reducing operations and setups wherever possible? I would say it is not a general manufacturability principle at work here. It really is what's superfluous. When people are making a brand new gun in peacetime, they tend to include some bells and whistles, some things that are kind of nice to have or make the thing look good. They're kind of like the equivalent of garnishes on a dish. If you go to a restaurant and it's high end and it's not super busy and they want to make a really good impression, the plating will be great and there won't be any little drips of sauce extra on the plate and there will be a nice garnish on it. But if all of a sudden the 100 people from some convention all show up at the same time and all need food right now, all those garnishes go out the window. It's the same base product, but there's a lot less time spent in the final polish and presentation. And that's a lot of what we see in firearms. You will often see almost always, you see lightning cuts scrapped. Like when we were first making this, we tried to cut every little bit of extra weight where we could afford it because it makes the gun look better in trials. And, and it is a genuinely good thing to make, if you can make that gun half a pound lighter without sacrificing anything. But in truth, what you are sacrificing is manufacturing time and cost. And if all of a sudden, oh no, we need 100,000 of these by next week, well, if we can increase production 5% just by skipping these couple of cuts whose purpose was only to make the gun a little bit lighter or a little bit prettier, or we come up with simplified versions of things like sights. The super adjustable hand cranked micrometer sight was great. See example, Thompson submachine gun. But nobody really needed it. It was just kind of nice to have there, and it let us charge a premium. And now we have to produce them as fast as humanly possible. Screw it. We're welding a fixed peep sight onto this thing. That's what guides those sorts of simplifications in firearms. Squid556 says, post-World War II saw an explosion in stamped firearms components. As time has gone on, we see fewer stampings. Has the relative cost of stampings increased from back then? My local stamping shop doesn't pay well. I'm not sure it's a high-profit business. I can't really speak to the economics of stamping in general as an industrial thing, but in the case of firearms, a lot of what we had in World War II and just after World War II, early Cold War, was like stamped receiver guns. Things like the Sten, sort of, but the grease gun is a really good example. It's a complex stamping. The Sturmgewehr is an even better example. Very complex receiver stamping. It allowed the use of low-grade steels. You don't need a lot of specialized alloys to make a good stamping steel, which was great for Germany at that point in World War II. That has transitioned to polymers. Polymers do a lot of that same work better and cheaper. So if you want a complex shape, it doesn't have to have a whole lot of strength within itself. That's polymer. That's molding polymer. The molds are easier to make than stampings because there's less force being put on them. The parts can be it's easier to make a complex molded part, polymer molded part, than it is to make a complex stamping. And yeah, the polymer technology has just overtaken stamping, I think. So that's why you see like the HK-UMP as a submachine gun, great example here. Compare that to a grease gun. They're really very similar, just the UMP has a polymer receiver, the grease gun had a stamped sheet metal receiver. We do still see a fair amount of stamping in firearms, but it's very small parts. It is things like if you can design a part to be flat and of uniform thickness, it's a really good candidate for stamping. So trigger connector bars, for example, rather than trying to mill a long, thin, narrow bar, stamp it. Get stamping steel of the appropriate thickness and just stamp out the profile and bend it, put a couple of bends in it in the right places. You know, simple one-dimension bends. You can make, like, stamped parts are still very economical and make a lot of sense, but it's for small parts typically, not for complicated things like receivers. SB says, now that Venezuela has been liberated, I know there is an entire Russian-built and supported Kalashnikov concern, AK-100, maybe 200 and 300 series production facility located there, with a history of South American arms manufacturers being readily imported into the US, think Taurus, Bursa, etc. Could we ever see imports from this manufacturing facility? I'm going to go with probably not. The AK market in the US is pretty well filled. It's not like we have a lack of people manufacturing and importing AK variations. Not much has actually changed in Venezuela. Like, Maduro was removed, but his government's still in power, at least as of the time of this recording. There's not necessarily a lot of incentive for a Venezuelan government factory to ship guns to the US commercial market. There are still significant legal hurdles to importing, foreign-made AKs. You want to talk about a US company investing money in Venezuela? That's a pretty risky business. Historically, that's been a really good way to lose your entire investment. And there is a small core group of people who appreciate like an actual Russian licensed AK-100 and would love to see those guns. But then there's the 99% of people who are buying AKs for whom a Romanian-made, what are they now, $600? Like a low-end Romanian-made AK is great. Like, and if you offer them a true Russian AK-100 for 3 times the cost, which is what it would almost certainly be, they're going to look at you like you've got 3 eyes. Like, why would I buy that thing? I can get this Draco for 1/3 the cost, and it's great. Actually, it looks cooler because it's smaller and it looks mean. So no, I do not see us getting Venezuelan import AKs anytime soon. All right, we have now entered the 3D printing zone. I have several questions here that I lumped together about 3D printing. So we'll start with Taylor. It says, do you think that in a reasonable amount of time we will see smaller scale, consumer-grade metal 3D printing machines that one can use in a home garage workshop? Absolutely. I have absolutely no doubt that that will happen. Like, we've already seen that happen with polymer printing. It wasn't that long ago that a 3D printer out of polymer was a large industrial thing that cost a whole lot of money, and you needed to have some really good, business case to afford and justify. And now home 3D plastic printers are very affordable, very small, readily accessible. Absolutely the same thing is going to happen to metal printers. We've seen them increase dramatically in capability. They used to be really only kind of capable for experimental, prototypey, proof of concept sorts of things. If you want a good example of this, like go back and take a look at the video I did with Cy Hudson. He brought in a couple of 3D printed Hudson prototypes, and they look really quite rough. Like the surface finish isn't very good. And referencing back to a few questions ago, those machines' capability for precision was limited. Maybe all you could get was 1 to 10. If you needed a part that had to be a 4 to 6 in dimension, your 3D metal printer wasn't really capable of doing it. And we've seen 3D metal printers get phenomenally better. And that's obvious from looking at the 3D printed suppressors that are on the market today. Those have very good tolerances and making very complex shapes. And I have absolutely no doubt that that will trickle down. Just like home computing technology, oh yeah, it's absolutely coming. Toby says, with 3D printing now being more and more a part of the manufacturing process and 3D printed suppressors showing that it can be used for more than just prototyping, do you think we will see it used in more ways in firearms parts themselves? What application other than suppressors do you think could really benefit from 3D printing's ability to make highly complex internals that could otherwise that would otherwise be extremely difficult to do with traditional manufacturing? Like off the top of my head, I don't see a whole lot of places where 3D printing will make a huge impact on firearms manufacturing. For prototyping, absolutely. For making, it's far more efficient and effective to make all of the parts for a firearm if you are experimenting with its design. If you need to make version 1 today and version 2 tomorrow and version 3 the day after that, it makes sense to 3D print all of those components. But what it means is you're going to spend a lot more time making some simple thing. Let's say you have a basic stamped trigger bar, which in mass production, you're going to laser cut or just stamp out of a piece of sheet steel, put 2 bends in it, drill a hole, done, good to go. Actually, like the hole comes in the stamping process. You can 3D print that thing too, and it'll take a lot longer to make one part by 3D printing it than it would take to make a whole sheet of them in a production facility. But you only need one, and you don't know if you've got the dimensions right yet. So you 3D print one, assemble it together, make your revision, 3D print a second one, make a revision, boom, okay, that's our final design. Now we set up the tooling to stamp these things out for production. For that, 3D printing is phenomenal, and it'll be used on every component, virtually, of handguns. Probably, I don't know if they can 3D print springs effectively yet, but sooner or later, they will. However, like suppressors are kind of this weird edge case where a functioning suppressor, or a suppressor's functionality, can be made substantially better by the use of these really complex calculated internal geometries and shapes that are impossible to make with traditional machining. And so suppressors are this perfect place to use 3D printing. With firearms, most of our internal components are pretty straightforward, and they don't actually benefit from 3D printing. Like 3D printing is not a magic improvement to everything. Just like no other manufacturing technology is a magic solution to everything. Like forging. Everyone knows forging is great. Excellent parts come out of forging. Well, would you do a forged plastic buttstock on an AR? No, it just doesn't make sense there. Would you do a forged heat shield for the inside of the handguard? No, it doesn't make sense for that application. And 3D printing doesn't really make sense for a lot of firearms parts. I could see maybe someone coming up with a complex trigger mechanism, maybe, but even that, I'm a little dubious. Nothing jumps out to me as really obvious. Maybe some optics applications. If you want to have a very small, complex internal geometry to hold, say, the LED in a red dot sight, inside some element that can then be moved for zeroing, maybe that's an application for 3D printing. But that's about all I can come up with. Then our third 3D printing question comes from Philip, who says, with the recent advancements in AI and 3D printing, do you think that we'll see teams having better success in reproductions of underdocumented or completely lost designs altogether? I'm thinking of the ability to scan parts and run them through AI models that would help determine metallurgy and functionality without having to make physical prototypes. So 3D printing, yes, absolutely. For all the reasons we just talked about. Someone can mock up the design, create the models, 3D print one out, see if it works, see what needs to be changed, and iterate that way. I don't see the AI being particularly useful in this case because, again, AI is not a magic tool. The AI that we have today are large language models. They are trained on the contents of the internet, and then they are essentially predictive engines answering questions about the information that they've been trained on. And there, as we will get to in a question coming up here, there's not much out there on the internet about firearms metallurgy and firearms design engineering. Grok doesn't know that much about how to make a firearm because there just isn't that much printed on that sort of thing. In the medical space, we have a ton of like research papers on medical issues that are published and accessible, and large language model AIs can access them. We don't have that sort of literature database on firearms manufacturing because, frankly, it's all sort of internal. I want to say it's like corporate secrets, but there's not a big market to publicize it. If a company develops, company expertise on this sort of stuff, it behooves that company to keep it to themselves, to keep the advantage in-house rather than just share everything they discover with everybody else. So AI is not in a position to actually know more about this sort of work than a proper, experienced firearms design engineer. That's the sort of person you want on that project, who can look at a thing and go, trunnions. We're going to make the trunnions out of S7 tool steel because it's good and hard. Or, we want to use this for barrels. What's the difference between a button rifled barrel and a hammer forged barrel? What's more appropriate for this particular one? That's a question that is much better suited to an experienced engineer than a large language model AI robot. Let's see. Here we go. Tomac says, can you recommend any good books or sources to start understanding the unique challenges of both the manufacturing processes as well as the business side of gun manufacturing? Sadly, Tomac, the answer is no, I cannot. There are very few books written on this subject. There are a few on the engineering and design of firearms, and I've done book reviews on a bunch of them. Most of the ones that I'm aware of, I've done book reviews on here on the channel. But as far as books on getting into the manufacturing business of firearms, there just really aren't any. So, sorry. The answer to that is the way to get this understanding is to get a job at a firearms company and build the experience yourself over many years. That's how it's going to work. Bob says, hello Ian, this is a goofy question, but still a good brain exercise. I was doing a bit of daydreaming the other day while cleaning an AR, and the thought occurred to me, what if Eugene Stoner back in the 50s had stayed in the aircraft parts design business and never desired to design firearms? That means no AR platforms or architecture. Where do you think we would be today with our military? Who would be the main players in supplying rifles, carbines, machine guns, etc.? Honestly, while the details would change if Stoner had decided not to make the AR-15, I don't think much else would be fundamentally different. Stoner was the first person to apply a number of things together in a good way. Things like fiberglass and aluminum applied to the firearms space, but he was not the only person doing it. And there's no reason, if he hadn't done it, that someone else would have. And we have examples of, certainly plenty of examples of aluminum in firearms manufacture. Like 1957, the same year the AR essentially is born, the AR-15 is born. We also have the Whitney Wolverine, which is an aluminum 22 rimfire pistol. All of these things would have happened sooner or later. They might not have happened, well, they wouldn't have happened in exactly the same way, but I think without Stoner, the US still would have adopted a small intermediate cartridge simply because that fit the changing role of combat, and we saw the way on that from the Soviet Union and from the Germans in World War II, and sooner or later we would adopt it regardless. What companies would be at play? Well, I don't think, there have been plenty of times when even Colt and Armalite are not involved in US military firearms manufacturing. We buy a lot of guns, or we did, from FN. FN would definitely still be a key player in the role, in the space, having been there long before Stoner, and has been there well after Stoner as well. Eric says, what in the process of manufacturing ammunition makes some brands more accurate / reliable than others? And how do firearms companies factor in these variances so their guns work well with multiple brands of ammunition? The first half of that is basically all the same elements that we've already talked about for parts manufacture. Ammunition is all about consistency. I mean, all manufacturing is mostly about consistency, but with ammunition, it is particularly exaggerated. Everything is, does your ammunition fit the tolerances set out by a body like SAMI of here are the official standard acceptable dimensions for whatever cartridge. And the better the ammunition is, the closer it's going to adhere to all of those standards and even exceed them. So your really precise match ammunition means that the bullet weight is made to a tighter tolerance, so there's less variation in bullet weight than is allowable by the general industry standards. There's less variation in powder weight and powder formulation and powder grain size, all of which change the burn rate and the pressure and the eventual velocity of the bullet out the barrel. It's all about consistency. So the more expensive the ammunition is, the more components they're going to be, well, the more high quality the ammunition is. Either they're using more expensive manufacturing tools so that they don't have, everything's made to a tighter tolerance and they don't have to throw it away, or they're using the same sort of tools as everyone else, but they're willing to scrap a larger percentage of those outliers on their bell curve of dimensions. That's it. Now, how do gun manufacturers deal with variability in ammunition? Largely by tearing their hair out over it. This is actually a huge issue, and it's a big issue, especially for cartridges like 9mm Parabellum that are so ubiquitous and have so many different variations, and there's ammunition from so many different places and different times, and a lot of the customer base doesn't recognize that. They just think 9mm is 9mm, and I should be able to buy a box of 9mm and stuff it into a gun and it should work, or else obviously the gun's crap. Not considering the differences between things like heavy subsonic 9mm with heavy bullets with a large fat curvature at the front versus super light high velocity loadings that have a very small bullet versus hollow points where the front geometry is totally different. The only way manufacturers can deal with this is through extensive testing. Redesign, test, get the widest variety of ammunition in during the manufacturing process that they can find, and just experiment with all of it. And there are going to be times when it's like two ends of the spectrum simply cannot be accommodated at the same time. There are going to be guns, well, for example, if you want to be able to run hot ammunition and underpowered ammunition at the same time, you're going to have to basically set the gun up to work on the lowest powered ammunition that you want to be able to tolerate, and then accept that the high powered ammunition is probably going to give you excessive bolt velocities. Like if it's a gas operated gun and it's willing to work on ammunition that's a 3 out of 10 power scale, and then someone loads a 9 out of 10, what's the gun going to do with all of that extra energy that it doesn't actually need to cycle? Well, you're going to have to make sure that the gun's strong enough that when the bolt hits the back of the gun moving a lot faster from a high pressure round, the gun's strong enough to absorb it. A classic example of this not being the case would be the Smith & Wesson 1940 light rifles, designed for a relatively sedate 9mm loading here in the United States by Smith & Wesson, then sent over to Britain, where they were used with a high-pressure submachine gun loading, and it didn't work, and the receivers cracked as a result of bolt impacts on the back of the receiver. They didn't have all the right ammunition to build the design around. If you're designing a gun to use a proprietary cartridge, everything gets so much easier because you get to control the details, the dimensions of the ammunition and the firearm, and you can make sure that they all work together. Once something's out there in the common world being manufactured by a whole bunch of people, you're kind of at the mercy of the whole market. Another good example of this having impact would be Daniel Defense. When they reintroduced the H9, right out of the gate, they started getting complaints of keyholing bullets. And it turns out that there were I think there was one specific loading of ammunition that just didn't play well with their polygonal rifling design and tended to keyhole. And it just wasn't a brand that they'd happened to test because it didn't seem to be an outlier in any other way. What do? Like, it's, on the one hand, they would have been perfectly justified in saying, in theory, in saying, don't use brand X because it doesn't work because it's wrong and it doesn't meet the overall spec of 9mm ammo, and we shouldn't have to design around it. But the reality is the customer base expects the guns to work with any ammunition. Customers are generally not willing to discriminate amongst ammunition brands because of a gun's preferences. They need the gun's got to work with everything or else the gun's crap. And so Daniel Defense essentially just had to, the practical answer is they had to recall the guns, change, what they ended up doing was just replacing the barrels. They got rid of the polygonal rifling entirely, went to a traditional cut rifling. That removed that problem, and that solved it at significant expense to Daniel Defense. Let's see, Hazel says, do you have any of your own firearms designs that you would like to bring to mass production if the process wasn't so difficult and expensive? Nope. No, I do not. I actually get asked this question quite a lot. I'm largely interested in historical firearms and where they came from and what impact they had on historical events and that sort of thing. I honestly, personally, I do not have a huge drive to go out and design my own special fancy thing. And that's encouraged by the fact that I've studied so many different firearms development processes and stories that I recognize how difficult this is, and I'm not really interested in throwing my hat in the ring to try and make a new firearms design work. We'll get to some of this again in a minute, but the short answer to this is I really don't have any interest in making my own gun. Let's see. Cole says, metallurgy is often credited as being crucial to the advancement of firearms technology, yet is rarely discussed beyond that or in any detail. What are some specific metallurgical advances which have greatly contributed to firearms development? What alloys and treatments were most revolutionary for their time? Well, the biggest one is going to be steel. The development of our ability to process iron and steel. So at the beginning, it kind of comes down to alloying elements into iron. If you add in the right amount of carbon into iron, you get steel, and steel is massively stronger than iron. So early in firearms development, there were advances, industrial discoveries of how to shape iron, how to cast iron. You get things like, you'll see these labeled on gun barrels from the 1800s, Flussstahl and Kruppstahl, like the specific steel casting processes that were used to make steel and iron. Then, of course, from iron you get steel, and then there is a lot of research and development of alloys of steel. It turns out if you add small elements of various other, small bits of other elements into a steel, you can get significantly different material properties out of that steel. And so you can get steels that are particularly well adapted to stamping, where they're going to be malleable and flowing and bending around curves. You can get some that are that have a very great capacity to take pressure and return to their original shape. All sorts of different things. There is a specific book, actually, that I would recommend if you are interested in this. It is called Fighting Iron, a Metals Handbook for Arms Collectors. It seems like this is actually purpose-built to answer this particular question. So I believe this is actually out of print now. It was originally published by Mowbray. I'll include a link to it in the description text, but I think they're all secondhand now. So whatever link I put up is probably going to be quickly purchased, and then you'll have to go find your own copy of it. But really cool book, does a great job of covering this subject. Highly recommended. Had a question from two different people, and actually I've gotten this question a lot in the past, so I'm glad it's here. Both Matt and Paul essentially said, why are functional, reliable, and durable detachable box magazines so hard to produce? If you don't know it, box magazines are perhaps one of the very hardest parts of a gun to actually design and manufacture. And the reason for that is that we have incredibly high standards in a number of conflicting areas. So we expect a box magazine to be insanely perfectly reliable, like how many malfunctions per magazine are you willing to accept? The answer is like 0. Like if it malfunctions once every time you use it, that's trash. And it's actually a question of, well, how many fully loaded cycles of this magazine am I willing to let it malfunction once? You know, if I use this magazine twice, like every other time statistically, 50% of the time I get a malfunction, that's also trash. I need this thing to be like, I don't know, is 10, one malf in 10 cycles good enough? Probably not. That's still considered not very good reliability. So we have a very high standard for it to work. Remember that every cartridge in a magazine is operating under slightly different conditions. As you load rounds into a mag, you're compressing the spring. So when the top round, when you've got 30 rounds loaded in an AR mag, is under quite a lot of force from that spring compressed tight down at the bottom. Whereas the last round, if you've only got 1 round loaded in it, it's got a lot less force operating on it. The rounds coming from the left and the right are working differently. You've got 2 different feed lips. You have a follower that is non-symmetrical. So if you've got 1 round in the mag versus 2, the geometries are going to be a little bit different in how those rounds are presented. And again, we expect an insane level of reliability from this thing. We also expect it to be extremely cheap. If I told you, like, I'm going to build this multi-part mechanical device that uses changing spring pressures to perform, to present a cartridge in exactly the same way every time, and you're going to decide that your life will depend on this thing working right. If you weren't familiar with firearms, it would be very easy to assume that, okay, we're going to spend like $1,000 on this device. You know, we're going to have a lot of redundancies. We're going to put a ton of work into making sure that everything fits just right and all the tolerances are just right to make sure that it works 1,000 times in a row without a single hitch. No, actually, we expect this thing to be $25, like at the high end. If it's brand new, 25 bucks. I expect to be able to go buy an AR mag for like 10 and have it work too. If I buy an AR mag for 10 bucks and it malfunctions, garbage, like just wasted all my money. That's like, we have very high expectations and a very low tolerance for what we're willing to pay for this thing. And then add on top of that, the cartridges that it's going to be feeding are always going to be different. Most of the time, most of the magazines we're talking about here are for widely manufactured cartridges, 9mm, 5.56, 22 rimfire, 7.62 NATO, like cartridges that have been manufactured all over the world for hundreds, decades, if not 800 years or more. Different bullet weights. Sometimes they're going to be made out of brass, sometimes they're going to be made out of steel, sometimes they're going to be made out of aluminum. Maybe we'll start making them out of polymer. And it's this one magazine has to work with all of that stuff, all of it. And it has to work to an insane level of reliability, and it has to be cheap. That's why they are so difficult to make. Now, it is a matter of, in order to make it cheap, you basically have to be making it as either a stamping or a polymer mold. And maybe a combination of the two, if you have polymer with metal reinforcements set into it. So you're talking about tooling that is expensive to manufacture. You have to get that tooling exactly right. This isn't like 3D printing where you get to, like, I mean, maybe it could be. At some point, we'll be able to 3D print stamping molds. Probably high-end companies can already, but that'll probably help. But you spend a lot of money making a very precise stamping tool, and then you stamp out some mags and see if it works. And those mags have to be exactly right. You have to have the ductility in the feed lips just right. The heat treat has to be just right. You know, too soft, and the feed lips will bend under full pressure from a stack of cartridges. Too hard, they'll crack if you drop them on the ground. It's really, really an acquired skill. There are a few companies out there that are really good at doing it. And when you're trying to design a firearm, getting all of those geometries exactly correct without making it a very expensive part is really hard. All right. Makovet says, the Roswell Rifle Works guy, actually guys, are smack in the middle of what is essentially a passion project to bring the SR3M, that is a Russian 9x39 rifle, which is pretty darn cool, back to life. This is a hugely challenging project with a failure rate of similar projects very high. What advice would you offer to Roswell Rifle Works to increase the odds of the rifle not only making it to market, but becoming a viable product and a successful business? I actually did talk to these guys fairly extensively at SHOT Show. I'm excited about this project. They seem to be doing better at it than anyone else. There have been a number of failures in essentially this sort of project before, kind of like the Sturmgewehr. That's another one that has proven very difficult to effectively reproduce. At any rate, the first thing I would say to a person who is planning a reproduction firearm like this is to go into it with an accurate expectation of what the market is. The SR3M, for example, is never going to be a mass market common firearm. Its value and its interest lie in its historic position. And as a reproduction gun, its value comes from how closely it replicates the original historical item that is of interest. So if I want, the SR3M, by the way, it's 9x39, it's developed, it's intended to be used with a suppressor to make a very quiet, sentry eliminating sort of rifle. Well, if I just want to take that end goal and provide a firearm to do it, there's a ton of stuff out there on the market already that can do it better than the SR3M. The SR3M was designed a couple decades ago. It has shortcomings in ergonomics and sight accessibility and all sorts of various elements. I could go buy something brand new today, like a Honey Badger from Q or a Rattler from SIG, that are going to do the compact, quiet carbine thing better than an SR3M. But there are people who will absolutely pay more for an accurate clone of an SR3M than any of those other guns because they like the SR3M, they like the history. I'm certainly a person who falls into that category with a bunch of historical reproduction guns. Like, you know, one of the Smith Machine Group's FG42 reproductions is not as good of a rifle as many other rifles that are out there that do the same thing. You know, I want to shoot 8mm Mauser or 7.62 NATO from a detachable magazine with iron sights, I guess, because that's basically what those things use. There are guns that are lighter, better, more reliable, more ergonomic, and a heck of a lot cheaper than the FG42s. But I want an FG42 because the FG42 is cool. So if I'm going into that project, I need to have a proper understanding of how many people I can actually expect to be interested in this gun and at what price point. And like, that's the beginning, is customers times price equals here's the total amount of money that I might be able to generate from this project. Can I do this project for that amount of money and still have some element of profit margin left? And if the answer is no, don't start it. Now, making that calculation means you have to recognize, you have to be able to accurately predict what's involved in taking on this project. And that's where most people fail. They look at it and maybe they overestimate the number of people that are going to be interested, but more likely they underestimate the difficulty in doing it. And that's where these projects fail. We see that, I'm sure that's what was the root cause for the Automag failing again. The reproduction Automag guys have gone under, I believe. And it took, like, the design took more experimentation and more iteration and more revision than they expected, and maybe never got to the level of reliability that they needed it to in order to be able to actually sell it to their customer base effectively. So understand your market before you get into something like this. And then at that point, like, if you understand the market and you understand what is actually going to be involved in making the gun, then you're in a position, you're set up for success. Or you recognize that this isn't viable and I need to change the plan somehow or do something different. That's when I get emails from people saying they have a cool gun idea and they like to get some help with it. That's always my starting point, is who is actually going to buy this, and are they going to buy it for enough money? Are there enough of them? They're going to buy it for enough money to actually make it, like, does this come out as a positive number? Or are you already setting up a plan that will lose money? Because if it's going to lose money, either it has to be such a passion project that you're willing to lose money on it, which is a thing in the tech industry. Promoting a new product by selling it for less than it costs you to make it is a very viable technique. But reproduction firearms companies generally do not have the sort of bank account necessary to say, like, we're going to sell SR3Ms at a 70% loss for the first 5 years until the market demand catches up, and then eventually we make a profit on it. It doesn't work that way with reproduction guns. All right, Larry has a rather complex question. Let's see if I can tackle this one reasonably well. Can you compare some of the pros and cons of some of the popular firearms manufacturing techniques, i.e. milling, stamping, 3D printing, injection molding, metal printing, etc.? So standard ones, let's see. Milling is sort of your default. Milling is where you start with a solid block of metal and you cut away bits of it with typically a CNC machine until you end up with the shape that you want. It's not the fastest, it's not the cheapest, it's not the, like, it's kind of middle of the road on everything, but you can make most things through milling. Classically, like historically, when there are plans to make a stamped gun, but they want to make like one proof of concept first to see how it all works, you can actually mill replicas of stamped parts. In fact, actually, backstepping just a moment, that SR3M that Roswell is making, they are making their stamped top cover by milling it because it's very expensive to make dies to stamp out something like this. It's also pretty expensive to mill them on a part-for-part basis, but if you only need a small number of them, it's actually more cost-effective to just mill a copy of a stamped component. So anyway, you can make almost anything with milling, but it's not going to be the fastest, not going to be the cheapest way to do it. Stamping is, let's see, so stamping can be very high volume. It allows you to make very complex parts in a single or maybe a 2 or 3 stage process, but it allows you to make a very complex part very quickly. Like you have your complex mold tooling and you put a piece of sheet metal on it, you got your negative mold on top, your positive on the bottom, or vice versa, and you squish it together and the metal gets squeezed into a new shape, retains that shape, boom, it's all done. On milling, if you've got 18 different curves on a part, that thing has to go through one at a time and mill each curved element one at a time. Stamping, they all happen simultaneously. However, stamping is as much an art as it is a science. Getting the exact right alloy of metal that will flow around corners, the tightness of radii, the depth of stamping, like a drawing. If you've got a flat piece of paper and you're going to turn it into a deep shape, how deep are you drawing that metal down? Too deep, it'll crack. You'll get tears in the metal. You'll get tears at corners. Metal will pull in places. You know, if I'm making this deep part, where is the physical material for that deep part coming from? Is it coming from this side or that side? Some of that can be modeled. Some of it's experience and just long practice and know-how of, okay, in order to make this part, you'd think we want a square piece, but we actually want to make it bigger on this end because that's where it's going to draw in the material for this particular feature. Those molds are expensive to make. You'll often have to revise those molds. They don't have an unlimited lifespan. But if you're making things in large quantity, you want tens of thousands of a part, stamping, complex stamping can be an extremely cost-efficient way to do it, which is why it became so popular for that brief period before we got plastic molding, which does a lot of the same sorts of things. Obviously, like in our situation here, the benefit of polymer molding is it makes low-cost, high-volume, complex parts very quickly and easily. The molds are very expensive to make, and the downside is you don't do it with metal because it's polymer. We do have casting and injection molding, which allow you to make complex shapes with molten metal. So you can make a really complicated, weird shape because you're filling it up with molten metal. It's for solid objects, not for thin sheet. And there are a lot of engineering expertise that has to go into the design of molds in areas where you wouldn't necessarily think about them. So you want to make sure that there's proper airflow out of the mold so that when you pour metal into the mold, the air that's already in there can escape quickly enough that you don't get, well, first you don't get bubbles trapped through what's the flow of metal through your complex mold? Is it going to trap air any place and leave you with voids? Is it going to, is there enough opening on the outside to let the air escape so that you don't essentially create pressure in the mold and your part cools too much before it's actually completely filled? Does it cool at an even rate? How does the metal shift? How does it contract when it cools? Your mold isn't a perfect mold of the final part. Your mold is a mold of what you need to fill with molten metal that will then solidify into your final part. So again, complicated engineering expertise that has to go into manufacturing that sort of mold. Casting generally gives you a subpar surface finish. If you need very exact, precise surfaces, what you will typically do is cast the part and then machine the casting. A good example to look at for this would be the German G43 bolts, or actually bolt carrier, where the top of that bolt carrier looks like garbage. It is a very rough cast finish, but the underside elements, where it's actually interacting with components, they have milled to get the exact dimensions that they need. That's typical of casting. You can often recognize cast parts because the surface finish is better today than last ditch 1945 Germany, but you can still recognize the texture of a cast part because some surfaces, like again, going back here, the front sight block on an AR is a cast part typically because it's a great technique. It's a great manufacturing method for this part. You can get all of the weird odd shapes without having to take a machining cutter around into all of them. You just then go in and finish machine the parts that you need, like the inside of where the barrel has to fit. You drill a hole for the gas tube, drilling and tapping a hole for the front sight post, that sort of stuff. But the rest of it, who cares? It doesn't have to be very precise. Casting works great. Metal printing, we've talked about metal printing, has some real benefits for rapidity and iteration. It's very easy to change a dimension and create a new part. Once you get into, okay, I have my final dimensions and I want to make a large number of these parts in a short amount of time, 3D printing is only viable if it's a very complicated part that you can't really make with any of the other methods. CNC machining is generally going to be faster than 3D printing unless you're doing something really weird like the inside of a suppressor. My gin and tonic has gotten rather watery, but we're just about done here. So that's pretty much it. Kind of like milling is your standard. Stamping was the non-pressure bearing complex parts done rapidly that has been overtaken by polymer molding. 3D printing is still sort of a specialized thing. Milling remains sort of the bread and butter de facto go-to method. Forging, by the way, is similar to casting, except done under very high pressure. So casting is you're basically pouring molten metal into a mold and it solidifies and that's your part. Forging is you're taking a block of very hot solid metal and you are slamming it into a shaped mold so hard that even though it's not liquid, it squishes itself into a new shape. And this has implications for basically the crystalline structure of the material that you're forging, steel typically, and tends to be stronger. So none of these processes are necessarily better or worse. They have to match the requirements of the part that you're making. So for example, a forged AR gas block would be fine. Like it would be stronger than a cast one, but you don't need it to be stronger. Like you gain nothing in real practical application from having that part be forged because cast is perfectly good enough. A way to think about this would be packing materials. Some things get shipped to you in a plain one-layer paper envelope. Some things get shipped to you in a heavy cardboard box with reinforced corners and big stapled, the flaps on the top of the box are stapled together instead of taped. That box is super heavy duty and very strong, but I wouldn't put a letter in it, right? I wouldn't take if I'm gonna order a computer monitor, I'm not gonna take that and put it in a paper envelope, it's probably gonna break. That doesn't mean a paper envelope is a bad shipping material, because if I want to ship a letter, perfect. That is absolutely economized for a paper envelope. It's not going to get damaged, even though a paper envelope is insanely weaker than a giant reinforced box. So similar thing with machine parts in general and firearm parts in particular. There's no better or worse manufacturing method. There's only how appropriate that manufacturing method is to the part that you're trying to make with it. All right, and that wraps it up for us for this one. Hopefully you guys enjoyed the Q&A. I really like this. I wasn't sure how this particular topic would turn out, and lo and behold, you guys over on the Forgotten Weapons Patreon did a darned good job of submitting some questions that are quite insightful, and hopefully all of you guys watching learned something, enjoyed the process. Thank you to Kiro for sponsoring our Q&A here today. Once again, if you're interested in their gin or any of their fantastic rye whiskeys, you can get 10% off all of them at their web store. That would be a web store in the US, in Finland, or in Germany by using the code ForgottenGin10. I'll have a link to that in the description text below. Thanks for watching.